In the next couple of videos, we're going to be looking at the details of the cool operational semantics, going over the semantics of each individual kind of expression. We'll start with the easy ones and work our way up to the more complicated ones. So the easiest rules are the rules for the constants in cool. So the value true, the expression true, I should say, evaluates to a Boolean with the value true. And it doesn't modify the store, so the store is unchanged because it doesn't do any updates, obviously. And there's a corresponding rule for false. And integers are very, very similar. So if a integer expression, integer literal I, will evaluate to an integer object with the value I, and again, the store is not modified by such evaluation. And finally, strings. If S is a string literal of length n, then it will evaluate to a string object with the properties n and the string constant s. The evaluation of identifiers is very straightforward given that we have both an environment and a store. So to evaluate an identifier, and this would be a variable name like x or y or foo, what do? Well, first we look up in the environment where that identifier is stored. So that will give us back a memory location, L, sub ID in this case. And then we look up in the store what the value is at that memory location. So we use the same memory location here as an argument to the store to get back the value that variable currently has. And notice that just a reference, this is a read of memory, so this is loading, you can think of it as loading the value of the variable. This does not affect the store, so the store is the same before and after. This is just looking up the value of a variable, not updating the variable. The expression self just evaluates to the self object. So this is a place where we just make use of the fact that the self object is part of the environment. So that just gets copied over here as the result of the expression. And notice again that the store is unaffected by the evaluation of self. Now let's see how a slightly more complicated expression is evaluated, in particular the assignment expression. So an assignment consists of two parts: an identifier that is being updated, and an expression that is going to give us the new value. So for example, just to remind you, we might have something like x gets 1 plus 1. So 1 plus 1 here would be the expression e, and x would be the identifier. All right? And so in order to evaluate the assignment, the first thing we have to do is we have to know what value we're going to be writing into the identifier. So what is the update we're going to perform? So the first thing to do is to evaluate E. Okay? And notice here that E is evaluated in the same environment. So it has the same three components here as here. All right? So it just says the first thing we do is we run E. Okay, and that's going to give us back a new value V, or going to give us back a value V, excuse me, and possibly an updated store. So E can be an arbitrary piece of code. It could itself have assignment statements in it, and so the store that we get out might be different. All right, so E produces a value V and an updated store S1. And now, to actually do the assignment, what do? Well, we have to know what memory location we're supposed to update. So we look up the memory location for ID, and that'll give us some location L sub ID. And then we modify the store with the new value. We modify the store at that point with the new value. So we replace the location LID, or we update the value at the location LID to be the value of E, the value V. And we do that in store S1, which gives us a new store S2. And now notice that S2 is the store that results from the evaluation of E. Okay, so after we do the assignment returns the value V, which was, of course, the value of running E, and it returns the updated store S2. Next, let's talk about the operational rule for addition. So to evaluate E1 plus E2, what are we going to do? Well, first we're going to evaluate E1, and notice that that is done in the same context as the context of the entire expression. Okay, so the components of the context here for evaluating E1 are exactly the same as the components for the overall expression E1 plus E2. So when we evaluate E1, it's going to give us a value V1, and it's also going to give us an updated store S1. And then we're going to evaluate E2. And notice here that the context is different. The self object and the environment are the same, but now we're running E2 in the new store S1. And what that's saying is that if E2 has assignments or variable references in it, those assignments and variable references have to be done on the store that resulted from running E1. Okay, so it's very important that we get that any side effects that happen in running E1 are visible or that are seen by the expression E2. So when we run E2 in this environment, we're going to get out the value V2 and an updated store S2, and then the result of the entire expression is going to be V1 plus V2, and the resulting store will be the store S2. And notice here how the stores tell you the order in which you have to evaluate the expressions. So because E1 is evaluated in the same store as the overall expression, that tells you that E1 has to be evaluated first. And then because E2 is evaluated in the store that's produced by E1, that tells you that E2 has to be evaluated after you've evaluated E1. And then the fact that S2 is the result of the whole thing tells you that E2 is also the last thing that you evaluate during the execution of this particular expression. Okay, let's take a look at a statement block, and just for variety here, let me change my colors. So how are we going to evaluate a statement block of statements E1 through EN? Okay, well, so the semantics of this is that we should run them in order, beginning with E1, and the result of the entire execution will be the value of the entire block will be the value of the last expression. And this rule just says that. So first we evaluate E1, and notice that it's done in the same store as the overall expression, so that's what tells you it has to come first. And that produces a new store S1 and a value V1. Okay, and then E2 is evaluated in the store S1, and it produces a store S2, and so on. And then expression En is evaluated in the store Sn minus 1, and it produces a value Vn and a updated store S sub n. Okay, and then the result of the whole thing is the value of Vn and also the updated store S sub n. And this rule tells you the order in which you have to evaluate the sub-expressions. The dependencies here on the store force you to evaluate E1 and then E2 and then E3 and so on. So you have to do them in that order to get the side effects, the side effects in the correct order for all of these expressions. And furthermore, it also tells you that the only value that you're going to keep is the value Vn. Notice that none of the other values that are produced here are used for anything. They don't appear anywhere else in the rules. Let's take what we've learned so far and do a small example. So we want to know what happens when we evaluate the block. X gets assigned 7 plus 5. That's the first statement. And the second and last statement in the block is just the expression 4. And the first thing we have to do is to say what the context is in which we're going to evaluate this. And the context consists of 3 parts. There'll be a self object. And in this case, it doesn't really matter what's in the self object because self is not referred to in the program, and so it won't play any role in the evaluation. But we still need it because there'll be some self object out there. It just won't get used. And now we need an environment, which tells us the locations for all the free variables in the program. So we just need a place where X is going to be stored, and so X will be stored at some location L. And then we need to know what our memory contents is, what our store is, and let's just say that at L we have initially the value 0. Okay, so now we can use our rules to run this program or to evaluate this program. I'm going to make this line here much longer, and recall that the evaluation of a block consists of the evaluation of all the statements within the block. Okay, so the first one is going to be X gets 7 plus 5, and that will be evaluated in the same environment as the overall expression. So we'll have up here, the same context, excuse me. And I should say, I often slip, I realize, and say environment for the entire left-hand side of one of these judgments. I'll try to be consistent and just use environment for the second component of the context. Often in the literature, people call the entire thing on the left-hand side the environment, and that's why I make this mistake. But for this set of notes, I'm trying to be consistent. The entire, all the components on the left-hand side together are called the context, and the environment is just the second component, the mapping from variables to their locations. All right, anyway, coming back to the example, the first statement in the block is x gets 7 plus 5, all right? And then we're going to have the second statement as well, and we know that the self object and the environment won't change, but we don't know what the store will be. Okay, the store might be different, so we'll leave the store kind of empty for now. We'll figure that out later, and we're going to be evaluating the expression for. Okay, so this is the structure of the evaluation. Now to make progress, we should look at this first statement, try to make some forward progress on that one. So to evaluate the assignment, what do we have to do? Well, the very first thing we have to do is we have to evaluate the right-hand side. So we're going to have the context for that is going to be the same as the context we've been looking at all along, because that's the first thing that's actually going to happen, is to evaluate 7 plus 5. Okay, and now I'm leaving a little space down here for the rest of the assignment rule, which we're not going to fill in just yet. Now to evaluate the plus expression, we have to evaluate the first expression and the second expression. Okay, and so how do we do that? Well, we know finally, I think, how to do that, because we're finally down, we're going to have a single integer there, and that we already have a rule for. Okay, so an integer literal evaluates to an integer object. Okay, and inside that object is just the value. Okay, and the store is unmodified. All right, and then similarly for the other argument here. Okay. So the 5 will also evaluate to an integer object with a value 5, and the store will be unmodified. Okay, so that's the two sub-expressions of this addition. And so now we can fill in the result here. So we'll take the contents of the two integers, we'll add them. That will also be an integer object. So we'll get out the integer object 12, and the store has not been changed. Okay, so the store that we get out here happens to be the same as the store that went in, just because this expression had no assignments in it. All right, and now we're ready to do the assignment. Okay, so how do we do that? Well, we have to form a new store. All right, so we're going to have a new store, which will be L gets 0 with the value at L. I don't remember which way my notation went here. I think the number comes first, so we're going to put 12 in the location L, and of course that store is just equal to the store where L has the value 12. Okay, and so now what happens down here as we do the assignment, and we get out the new value. Okay, so the value of the right-hand side is 12, and we have the new store where the location L has 12. All right, so now we're ready to evaluate the second statement in the block, and that will be done in the store where L has the location 12. And of course, this is just an integer, and so that will evaluate to the integer constant 4, the integer value, 4, or integer object containing the integer object with the value 4, and our store. And it's just going to fit, not quite, right? And that's then the result of the entire evaluation. So this block will produce the value 4, an integer object with the value 4, and an updated store where location L has the value 12. So the next expression I would like to take a look at is the if-then-else expression. And to evaluate an if-then-else, what do we do? And actually, this should be an if-then-else phi, of course. So to evaluate an if-then-else, well, first we have to evaluate the predicate, and that's done in the same store, the same context as the overall expression. And if the result is true, if the Boolean predicate returns a value true, then we want to evaluate just the true branch and not the false branch. So that's why you only see here evaluation of E2 and E3 isn't mentioned anywhere. And just note here that the predicate may have side effects, and so E2 is evaluated in whatever store E1 produces. And then the result of the entire expression is the value of E2, okay, that's V, and also the final store that's produced by running the then branch. And there's a symmetric rule for what happens if the predicate evaluates to false. In that case, you would evaluate E3 and not E2. Next, we'll take a look at what happens with while loops in COOL. So there are two cases. First, if the predicate of the while loop evaluates to false, okay, well, in this case, the loop body is not going to execute. All right, so the first thing we do is we evaluate the predicate, and that's done in the same context as the evaluation of the overall expression. And if the predicate is false, then we exit the loop. And so the result of the loop is void, the value void, and just whatever store resulted from evaluating the predicate. The other possibility is that the predicate evaluates to true. So here we evaluate the predicate again in the same context as the overall loop. And if the predicate evaluates to true, then we're going to run the loop body once. Okay, and so we'll evaluate the loop body, and notice that that's done in whatever store results from evaluating the predicate. Evaluating the loop body is going to give us a value V and a new store S2. And then what we need to do is we need to go back around and execute the loop again. And how can we do that? Well, we're really just running the whole loop in the new context. So the next thing we do is we evaluate the entire loop, right, in the new store. So after we execute the loop body one time, then we go around and just evaluate the loop again. And now this may run for 0 or more iterations, all right? And when it finally terminates, if it terminates, it will produce a new store S3. Evaluating a while loop, of course, always produces the value void. And then what we'll produce for the entire loop, for the entire expression, is the value void and the updated store S3. The next interesting expression to take a look at is the let expression. So recall what this looks like. So a let in COOL has a variable that's being declared in its type, an initializer, which is optional. So this is the value that the identifier will be initialized to, and then the expression in which that new variable is available. So how do we evaluate this? Well, first we're going to evaluate the initial value of the new variable. So we evaluate E1, and as usual, that's done in the initial store, and it produces a possibly modified store. And now the question is, what's going to be the context here for the evaluation of E2 for the body of the let? And so it seems clear that it's going to involve S1 because it has all the updates from E1, but it also has to have this new identifier in it. And so how are we going to do that? So what we want is to have a new environment, E, but with a new binding of ID to a fresh location. So we're introducing a new variable. Remember that the environment has to track all the free variables. So this is one situation in which we're going to extend the environment E with a new binding. All right, and that location, the location for the new variable, has to be a fresh location. We don't want it to conflict with any other memory location we're already using. Okay, and so we're going to allocate a new memory location for the variable. And then the store, the new store, will also will be like S1. As we said, it has to include all the values for S1, but it's also going to have this new location for the variable, and that's going to have the initial value of the variable V1. To express that we need a new location, we're going to introduce a new operation on a store, which gives us a new fresh location. So new loc applied to a store is just going to give us some location that isn't being used by the store. So the store has a domain, remember it's a mapping from locations to values, and we'll just pick some new location that isn't in the current list of locations within the store, and that'll be the one returned, or that will be the one returned by newloc. Okay, so newloc you can think of as modeling the memory allocation function in the runtime system. So then here we can write out the rule. So this is the most complicated rule we've seen so far, so I'll just take a moment to walk through it. All right, so the first thing we do is we evaluate E1, the initializer for the new variable. Okay, so just like before, this is done in the same context as the overall expression, and this is going to give us a value for E1 and an updated store. All right, then in the updated store, using the updated store here, we find an unused location, L_new, okay? And then we're going to create a store where that new location has the value of E1. So we're going to store the value of E1 at that new location. We're going to update the store S1 to reflect that. And furthermore, we're going to extend our environment with the new identifier, which will be stored at this new location. And this is the context then, okay, with this updated environment and store, in which we evaluate the body of the let, which will produce a value V2 and a possibly updated store S2, and those are the results of the overall expression.